Last video, sums of discrete random variables, closed our story of the discrete world. PMFs answered every question we asked. This video opens a new chapter, because the discrete world is not enough. Noise voltages, waiting times, and signal amplitudes range over a continuum, and no list of values can hold them. The bridge is the cumulative distribution function. One object defined for every random variable, with 3 properties it must obey. We watch discrete variables draw staircases whose jumps are exactly their PMFs and meet the new citizens, smoothly climbing CDFs, the continuous random variables, plus the hybrids in between. Why does the machinery of the PMF run out? A spinner can stop at any angle, uncountably many outcomes, and the third axiom adds probabilities over countably many disjoint events only. We need a new object. Here it is. The cumulative distribution function of x at x is the probability that x is less than or equal to x. In terms of the sample space, it measures every outcome that x sends at to the left of x. It exists for every random variable, discrete or not. That is what makes it a bridge. Its shape is constrained 3 ways. Toward -infinity, the event empties, so the CDF falls to 0. Toward +infinity, it captures everything, so the CDF climbs to 1. Now take 2 points, x1 below x2. The event that x is at most x2 splits into 2 disjoint pieces, x at most x1 and x strictly between x1 and x2. Probabilities add, so the CDF can never decrease. Rearrange the same equation and you get the workhorse of the whole chapter. The probability that x lands in the interval from x1 to x2 is a difference of 2 heights, f at x2 minus f at x1. Now let a discrete random variable meet its CDF. If x takes listed values, its CDF at x just sums the PMF over every value at or below x. Watch the accumulation happen for an old friend, the geometric, with parameter p equal to 1/2. Sweep from left to right across its bars. Between values, nothing accrues, so the running total stays flat. Each time the sweep crosses a bar, the total hops up by that bar's mass. The result is a staircase climbing toward 1. Look at one step, its jump height is exactly the mass sitting at that value. So the PMF can be recovered from the CDF as the value at x minus the limit from the left. 2 descriptions, 1 random variable. Let us work the geometric in both directions. Its masses are 1 minus p to the k minus 1 times p. Summing the first floor of x of them telescopes into a clean closed form, the CDF is 1 minus p to the floor of x. And differencing hands the masses back, the CDF at k minus the CDF at k minus 1 collapses to 1 minus p to the k minus 1 times p, the PMF exactly. Not every accumulation climbs in jumps. Here is a CDF that rises in a smooth progression. 0 for negative x, then 1 minus e to the minus x. It satisfies everything we asked. It starts at 0, never decreases, and climbs to 1. When the CDF of x is continuous like this, and differentiable almost everywhere, we call x a continuous random variable. And continuity has a striking consequence. With no jumps, no single point carries mass on its own. Probability now lives on intervals. Mark 2 points on the axis, and the chance of landing between them is the vertical gap between their 2 heights. One more glance at our smooth curve. It is differentiable, with derivative e to the minus x, for x positive, measuring how fast probability accumulates. Hold that thought because that derivative is the star of the next video. One family remains, mixed random variables, whose CDFs climb smoothly in places and jump in others, like this one. They have no PMF, and they can be discontinuous at multiple points, yet the CDF still answers every interval question, as differences of heights. Next video, we differentiate the continuous CDF and meet the probability density function.